Hello everyone, my name is Yiling. I'm from Google and I'm going to present our research idea Synth2Aug, which focuses on cross-domain speaker recognition using TTS synthesized speech. When training a speaker recognition model, oftentimes we would like to have a large number of training speakers and prepare the training data which best represent the real-world examples. Although nowadays there are many public datasets available for us to use, these audio samples might not be close enough to the speech utterances the model is about to see at inference time. For example, if we train our model on red speech and run it on another domain, say speech queries such as what's the weather like today, it might not fit as well. There exists this target domain training data inadequacy. In order to address this problem, we propose the approach of generating TTS synthesized speech as an augmentation technique for speaker recognition training. While many popular augmentation techniques such as MTR focus on the audio environment, using TTS as augmentation is quite different and novel because it augments a new set of speakers. Here is the Synth2Aug system diagram we proposed. The goal is to represent the target domain as much as we can in all aspects. While the acoustic properties of the signals, such as the channel effects, would be difficult to capture, it is possible to learn and represent the target domain textual content. And for this task, TTS comes as a natural candidate. We train a multi-speaker TTS model. Using the closely matched target domain text we collected, we synthesize speech utterances with tens of thousands of distinct speaker voices. Next, we feed those augmented data into speaker recognition model training. The main observation from our experiments is that TTS synthesis could complement a well-tuned MTR setup. The model trained with MTR outperforms the no data augmentation baseline model by a wide margin. Moreover, TTS synthesis combined with MTR further introduces an 18% relative equal rate improvement over the MTR setup. Another interesting takeaway is that matching the target domain textual information is also very important. Please refer to the following slides for more details. This is the end of the highlights. Now I'm diving into the details of our experiments. Here is the agenda. TTS has already been widely used as an augmentation technique in speech recognition. As for the speaker recognition community, the most recent advances are related to anti-spoofing, where speech synthesis is used to examine if the speaker recognition systems are robust enough to spoofing attacks. It will be interesting to explore if a multi-speaker TTS system could be utilized in support of speaker recognition. Here is a brief comparison of MTR and TTS. As you can see, these two techniques tackle the data insufficiency problem from two different angles. MTR introduces noises and room reverberations, while TTS mostly expands the speaker variability. We are going to investigate the raw effects of each technique on speaker recognition performance, as well as the effects of both combined. This is our system for speaker recognition tasks. The feature extraction step includes a series of operations such as framing, windowing, FFT, and triangular filtering. There is also a voice activity detection module which removes the non-speech frames. At the end, the audio speech waveform gets transformed into the log-mel energy features. Our model is a text-independent D-vector model. The neural network has 3 LSTM layers with projections. There is a linear layer at the end to transform the RNN output sequence into a D-vector of size 256. The TTS model used in our experiments is a multi-speaker tacotron 2 model, which is composed of 2 components: a spectrogram prediction network to convert phoneme sequences to MEL spectrograms, and a wave RNN model to convert the MEL spectrograms to speech waveform. In order to support the multi-speaker capability, every speaker is represented with a d-dimensional embedding vector. This vector is a trainable parameter which is trained along with the main model. In addition, we introduced a sequence of 32-dimensional latent variables in the decoder to capture the intra-speaker style variations. The latent variables at each output step are sampled independently from a mixture of Gaussian priors. Following the variational autoencoder method, we train a recognition model from the output mel spectrogram to infer the posterior distribution of the latent variables. With the multi-speaker TTS model trained, we would have two approaches for speech synthesis. The first approach is to directly use the embedding vectors of the training speakers. The speaker embedding vectors we trained originate from real speakers, so we refer to this as real speaker embeddings. And the synthesis is simply based on what we just learned from those real speakers. On the other hand, there is another approach. Instead of using real speaker embeddings, we fit a mixture of 3 full covariance Gaussians to the set of training speaker embedding vectors, and then draw samples from the Gaussian mixture model. This allows us to extract as many voices as needed. However, there is a catch here. If we sample hundreds of thousands of speaker embeddings from this learned space, there will be a ton of embedding vectors which are really close to each other. As a result, the corresponding synthesized voices will be similar as well. Therefore, we conduct a speaker selection process. We incrementally build a speaker set in which voices are distant from each other. This would ensure that the sampled pool of the speakers are distinct. Last but not least, the transcript we prepared for speech synthesis is the text that closely matches the target domain text. We ended up with 4 datasets. The 128D real is the synthesized speech data generated from the 128-dimensional model with the real speaker embeddings, and the rest are the datasets with audio synthesized from sampled speaker embeddings. Let's listen to some of those synthesized speech samples.
What's the temperature in the living room?
What's the temperature?
What's the temperature?
What's the temperature in Chicago?
The training data here is the Libri TTS dataset, plus 2 additional proprietary corpora of over 2,000 speakers. There are around 500 utterances per speaker. This training data is super clean and is used for TTS model training. Note that this is also the training data used for the baseline speaker recognition model training. The evaluation data in our experiment is the target domain speech queries data. We prepare evaluation trial pairs to measure the model performance. For each trial pair, we compute the cosine similarity matrix of a test utterance embedding against the averaged enrolled speaker embedding. At the end, we plot the detection error trade-off, or the DET curve, and collect the equal error rates. We have made sure that there are enough trials for stability as shown on the slides, and the number of targets versus the number of non-target trials are balanced. There are 2 experiments we conducted. The first one is to measure the impact of TTS synthesized speech together with MTR, and the second is to investigate if changing the underlying transcript for speech synthesis leads to different speaker recognition performance. This is the first experiment. The baseline model is the model which we trained with the clean training data. As you can see, the equal error rate is very high. The following 3 models, TTS real, TTS sampled small, and TTS sampled, are the models which we applied TTS augmentation upon. We trained these models with not only the clean training data, but also different synthesized speech datasets. TTS real, as the name indicates, was trained with the 128D real dataset. TTS sampled was trained with all 3 sampled datasets, including both the 32, 64, and 128D. All of these 3 models outperformed the baseline model. You might have already noticed one thing. The total number of speech synthesis speakers used for training in the TTS sampled model is almost triple the number in the TTS real case. It will be interesting to have another model trained with similar number of speakers, with the only main difference being whether those speakers are from the real speaker embeddings or the sampled embeddings. That's why we have the TTS sampled small model here. Small refers to the case where we only have a small number of speakers, which is pretty close to the number we have in TTS real. From the results, the equal error rates indicate that introducing more speakers or more utterances with TTS would definitely be helpful. Furthermore, the ability to synthesize new speakers outweighs simply generating more utterances using existing real speaker embeddings. Now let's take a look at the results using MTR. The baseline MTR is the model which we trained with MTR data or noisified data. We have experimented with different MTR configurations and repetitions, and we ended up with 15 independent MTR repetitions. This model is considered as the baseline MTR model simply because it represents the best we can do with MTR, or only using the MTR augmentation technique. The equal rate is much better than the baseline model, as you can see. Here comes the question. Can we perform even better with the introduction of speech synthesis? One thing which we can do is we keep the original training data there while applying MTR on the synthesized speech. This is exactly what we have done in TTS sampled MTR, standing for applying MTR on the TTS sampled data. Well, why don't we just simply applying MTR on the original data as well? That is, we generate synthesized speech and apply a well-tuned MTR to both the clean original training data and also to the synthesized data. And that's what combined means in the last row. As highlighted, it gives us the best performance out of all the models. In the second experiment, we keep the combined model setup from the previous experiment and only change up the underlying transcript for speech synthesis. The names of the different model variations are pretty straightforward. Random digits are the tags of only numerical digits. Random words 104 have transcripts of randomly concatenated words, but just with different vocabulary sizes. The close match is the previous combined case, and exact match is using the transcript, which is simply a subset of the test utterances text. Here it is not the full set because the full set is pretty large, so we only take a subset. This would never happen in reality, but it is an interesting case to study. As for the exact match shuffled, the transcript is the same as exact match, except that there is an additional step of shuffling to reorder the words within each utterance text. Let's listen to some of those examples here.
434509.
Garden books serve to divorce gloves.
Lullaby direction, excellent wagons runs.
What's the temperature?
Where are you? Speed up.
Speed, where up are you?
Well, the equal rates are quite close, and it might simply be because of the fact that aside from different meaningful or meaningless synthesized speech content, there is always the original set of training data being used, right? So these data are clean and they could be masking things up. Therefore, in order to fully test the validity of those transcripts, we exclude the original TTS training data and train our model only on the synthesized data. In this way, we can see directly whether those different types of synthesized speech variations make sense or not. Wow, the numbers are quite different now. The exact match model again has the lowest equal error rate. This is no surprise because the synthesized utterances for training shared the exact same textual content with the test utterances. Comparing the close match model against the random words full model, we can tell that it is quite important to match the textual content of the target domain. Some random word concatenation is still better than nothing, but definitely not as ideal. More interestingly, the exact match shuffle model, which was trained with semantically meaningless synthesized utterances, is worse than the exact match model, but still better than the close match model by a very, very small margin. This may indicate that the benefits of matching the target domain tags stem from not only similar vocabularies and word frequencies, but also similar word sequences. In addition, there is a clear trend of an increased equal error rate when the vocabulary size is further reduced. In short, we suggest a sufficiently large vocabulary for the task. At the end, I would like to recap the main observations we have found from our experiments. We are excited to find the additional benefits of speech synthesis in the speaker recognition field. Even with some sophisticated, well-tuned MTR configuration, TTS as an augmentation still seems to be valuable in some aspects. From a broader perspective, our paper presents an initial study into how we can use data augmentation to better model the speaker-centric aspects of the speech data. It will be interesting for us to further explore and examine other ways in which speaker-centric data augmentation can be applied using TTS synthesis or other type of approaches. So this is the end of the presentation. Thank you for listening.